Is my screen visible to everyone? And am I audible?
Yes.
Okay. Um, so today we'll be looking at something called the standard template library. Uh, and we'll be looking at the algorithms and the data structures that it provides us with. Well, the data structures are actually referred to as containers, but we can call them data structures. No real difference. So what is the STL? So strictly speaking, it's really a part of the C++ standard library, and the STL, as we call it, was something different, which was later merged into the C++ standard library, but that's not really important to us. We don't care about that. It is called the standard template library because it uses a C++ feature that is known as templates. So templates basically, what they allow us to do is they allow us to write type independent code. For example, let's say you wanted to write some function for adding two integers. Say you wrote int f, int a, int b, and in this you return say a plus b. Now say you wanted to write the same function but for doubles instead of ints. So again, you would write double f and then double a double b and return ab. And now if you wanted to do the same thing for every single type, you would end up writing a lot of functions. And like then again, users may define their own types, and then it will be a mess because you will have a lot of types and a lot of different functions which are doing the same thing. So to overcome this, the C++, the people who created C++ came up with this thing called templates. And what template allows us to do is like they said just forget about the type and let's just write the function itself. So what they did is we write this thing template, then we write uh, type name t, and then we can just write t function ta, then tb, and then we can just write return ab. Here, notice that we didn't mention any type at all for a and b. So when the user is calling this function, what he will do is he will just write the name of the function, he will write the type that he's passing, and he will just pass the variables. And like this, he can again write like f double. So basically, it passes on the problem of uh, the type to the user. So that is very convenient for us because now we don't need to write hundreds of functions doing the same thing. We can just write one function and then the user can add in the type as he needs, which is very nice. And you will see this kind of syntax again when we are dealing with the containers. So I'll just briefly explain it there again so you don't get confused. Okay, now the STL provides us with many useful algorithms, which is like sorting, binary search, linear search, filling an array with some values, and many more. Plus, it also provides us with some containers. The most commonly used ones are vector, which is like a dynamic array. So in that array, we can change the size, we can add elements anywhere. So it's like an array that can be changed on the go instead of its size being fixed, the order of elements being fixed, and so on. Then we have set. Then we have set, which is like mathematical notion of set. Map, which is if you have done Python, maybe you know there is something called dictionary. So like it's an associative array, maps keys to values. I'll explain all this again. And then these you probably know, stack queue, then double-ended queue. Okay, so we will look at all of these one by one. First, we'll start with the algorithms and then we'll move on to the containers. So up to this much, does anyone have any question? And like, if you're having problems if that I'm going too fast, then don't hesitate to tell me. Is it all okay with everyone?
Yes.
Okay. Okay, then I'll move on to the next slide. All right. Now we come to something known as namespaces. Uh, Again, this namespaces is something you definitely haven't encountered in C because it's a C++ only feature. So what namespaces does is basically it prevents name conflicts. So for example, it is possible that you have two functions, say function one is just adding two integers and function this another function is subtracting two integers. Now you named the functions the same, but you don't know that you named the functions the same, and you've done this accidentally. So this can lead to big issues in big projects because you will have no idea where the error is, like which function is referring to. So namespaces is here to solve that problem. So what namespace does is you write namespace, then you give it a name, say uh, my funcs, right? And then inside this block, you just put all of your functions. Okay, f1, f2, f3. You write the syntax for all these functions inside this namespace, and then say your friend comes along and he also names his own set of functions which happen to be somewhat coinciding with yours. So he'll name it as say friend friends functions, and then he'll name his own functions which are the same. But now the thing is there will be no confusion because when you put something in your namespace, you will have to refer to it in this form as my funcs. Then you have to use this operator, which is called a scope resolution operator. So, I mean, a detailed explanation of this would be kind of irrelevant here, but uh, it just allows you to refer that this function f1 that I'm using, it belongs to my funcs. It is my function f1 that I'm referring to here. And then when your friend wants to use his function f1, he can refer to it as friends funcs, and then he can write f1. Okay, so uh, the important point here is that now there is no confusion. Okay, so namespaces you probably won't be using in most of your code, but it's just good to know. So everything in the C++ standard library is under this namespace that is known as STD. STD for standard because, well, standard library, so standard namespace. And that's why you'll often see syntax like STD, then scope resolution, then vector STD, scope resolution, cout. If you have seen code examples of C++ on the internet, you have probably seen this kind of syntax. And that is the reason for it. Because there is the namespace, which in this case is std, then you have the scope resolution operator, and then you have the function, or say container, or input output. Okay, so usually to avoid writing this std thing every time we have to refer to something, we use this line that is called using namespace std. So basically what that tells the compiler is that throughout this program, we are going to assume that whatever we use belongs to std namespace only. We do not need to write it again and again. Now, in general, in say development code, this is generally bad practice because if you assume you're using a namespace throughout a program and then you accidentally put in some other namespaces code and expect it to do that thing, then it will lead to a whole lot of confusion. But for our CP programs, the programs are really small, so yeah, we don't really care. We are okay with using the same namespace throughout. So if you have ever seen code, like some CP code, then you've probably seen this using namespace std. This is what it means. that we don't want to write std again and again, and we are just assuming that we are using std throughout. That's it. Any questions? Okay, I am assuming no one has any questions. So, okay, move to the next slide. Uh, Now we come to something called iterators. Uh, okay, so let me ask you, how many of you heard of pointers? Can you raise your hand once? Okay, it seems like a fair amount of people here have heard of pointers. Okay, okay, you can put down your hands now. Okay, so wait, right. So iterators is this concept that is similar to pointers, but it is not exactly pointers. I'll explain. So what an iterator does is that it allows you to move through a container. Like say in C, for example, you had some array, right? You had some array, say, of length 5, and you had say 2, 3, 1, 4, 5, and you had a pointer here. You had a pointer, say, A, and then you could just move the pointer ahead. Like you can just add to the pointer, and then it'll refer to this place, and then it'll refer to this place, and here, and so on. And then you could also do something called dereference the pointer, right? If you dereference the pointer like this, so A is this position, and star A is what this value is. So A is the position of this 2. A is position of 2 in memory, and star A, which is the dereference, this is called the dereferencing operator. This gives you 2 because it is star A means give the value of whatever is at A. I I think this much everyone knows from their C class at least. So iterators does a similar thing, but the thing is that when it comes to the standard library, like in array, you know that everything is stored in contiguous memory blocks. Means if this is at address say 123, the next block will be at address 123 plus whatever is the size of this. So if it is int, say it will be 4 bytes, so 127, and then say 131, and then so on. You get the idea. But for these things, like for the STL things, it is not guaranteed that they will always be next to each other, right? So it can be possible that they're all scattered throughout memory. So what iterator does is that iterator allows us to do the same thing as pointers. We can move throughout this container by just incrementing the iterator, like say iterator, then iterator plus 1, iterator plus 2. So like this, we can move throughout the container. Uh, the thing is that in modern C++, pointers are kind of considered unsafe. So using iterators is generally the best practice. Again, because everything may not be stored next to each other in memory like an array is. So in general, like broadly speaking, I mean, if you go in depth, you will actually find that there are 6 different kinds of iterators, but we'll not go into that much detail. For our purposes, like at this level, all you need to know is that there are 2 different kinds of iterators. One is called random access iterators. So, okay, yeah, let me just say, so there are random access iterators and there are sequential access iterators. So now I'll explain like what random access and what sequential access means. So say in an array, If you want to access what is at the, say, at the third position, then if this array is named A, you can just do A2, right? That will just give you whatever is at the third position. That is not a problem. Now, similarly, if you are using an STL thing, say, or say if you're using std vector, and again, if you have these things and you want to find out what is that position 3, right? So you can just write, if this vector is named v, you can just do v2. This is exactly the same as array. So in this sense, vector is random access, which means at random you can pick any element you want, right? You don't have to go one by one from the beginning or from the end. You don't have to go like this. You can access it in any order you want, anytime you want. So that is what I mean by random access. These iterators you can do a iterator plus x, where x is any positive value, and you will get whatever is there. So that is not a problem. So random access iterators are possessed by these things. These things are vector, which is basically a dynamic array. It's kind of the same thing as an array, but as I said, you can insert, remove anywhere you want. Then we have double-ended queue. Double-ended queue basically allows pushing and popping from any side of the array, but not in between. And string. String you probably know, just A, B, C, D, E, F, G string. So yeah, these allow random access. You can access any element at any point, anytime. Sequential access means that you cannot access that in any random order. So let's take an example of set, right? So in set, we have, say, let's say, I'm sure all of you know what a mathematical set is. It's just some values, right? And now in a set, like if I say, ask you what is the second value in a set, a priori you cannot just like tell me what is the second value in a set. Like it doesn't make sense. So like uh just by way of an analogy, like what I'm trying to say is that you have a start. Okay, so you have a start point, let's say here, and now you can only move to the left, right? Okay, or you can only move to the right. So if you view this as like these series of blocks, I can only start at here, then I can move left, then I can move left, then I can move right. But I cannot just randomly jump here or here or here, anywhere I want. I cannot do this. So you have to access the elements in a particular sequence, like for first, second, third, fourth, or from the back, say fifth, fourth, third. You cannot go 1, 3, 5, 7 like this. You cannot go like that. So that is something you must keep in mind. Uh, Again, I will elaborate on this more in the container section. Uh, One more thing to keep in mind is that stack and queue do not have iterators. So actually, you cannot see what values are in them. You can only see the values which are at the front, which are at the top. Like for stack, just you enter at the top and exit at the top. So you can only see this value. You have no idea what is here because stack and queue don't have iterators, so you can't iterate through the container and see. And again, in queue, you can only see what is at the front or at the back. You cannot see what is in between. Uh, any questions? Like this was just a brief overview. So like, yeah,
We'll elaborate the sequential one, right? That was a little confusing.
yeah. Can you say that again?
I'm a little confused about the sequential access. Like in
Uh,
set, why can't we uh, just take like
okay,
first point at one and then point at three?
okay. So there There are, okay, so the big reason is that internally set is not implemented as just an array. Set is actually implemented as something called It's something called a red-black tree. It's kind of a binary search tree. I'm probably drawing this very wrong, but the point is, like, the reason you cannot access it in sequential order is because it's actually a tree. It's not an array. So that is going to cause problems. That is going to cause big problems if you could just access anywhere. I will explain it again in the container section, so don't worry about it. Just know that you cannot go from 1 to 3 in set and map.
Okay, okay, cool.
Is it like linked lists?
Uh, Not exactly. It's like if you're talking about
Okay.
set and map, it's not linked lists. Linked lists are linear. Like you have this, then you have a pointer to the next element, and then you have sorry, you have a pointer to the next element. But in tree, you can have pointers to like multiple elements. So like
Okay.
yeah. Uh, I mean, trees are something you will come across again in graph theory, where they will be explained in more detail. For now, just don't worry about it. We'll come back to this later. An example usage. Right. So actually, maybe I think it will be better to cover an example usage of iterators after we have looked at STD vector at least. So I will skip this for now. We'll come back to iterators once we have done vector. Uh, Things to look out for. Again, I will come back to this after doing STD vector. Right now, it won't make much sense. Uh, so we'll just look at the algorithms first. So in algorithms, most algorithms you will find that they are implemented in the header files std, not sorry, not std, in this header file called algorithm and in this header file called numeric. In these two header files, you will find most of the algorithms are implemented. Actually, all of the algorithms that you will need. Uh, so like, I think the majority of these are, I think this, wait, I think these are in algorithm and these are in numeric, I think. But yeah, so if you're again, if you're using bit slash sdt std c++.h, you don't need to worry about this. But if you are including any of these functions, you need to include these two headers in case you're not using bits slash sd c++.h. Uh, so there are like, I think 14 functions here, but the list is in reality it's like much bigger than this. These are just the most important functions that you'll come across. So let's just go through them one by one and see. Okay, so stdsort is our first function and probably our most important function. So what stdsort does is it sorts a sequence. By default, it sorts in ascending order. Like say you have an, okay, let's say you have an integer array uh, of size 5, which is say 2, 4, 3, 5, 1. Right. Now, std sort, if you sort it, so the way you call sort is, so sort basically takes in, let me just write it here, sort takes in iterator 1 and it takes in iterator 2. Uh, in reality, the thing is that pointers can be converted to iterators. So if you just take, say, uh, like R and you take, let's say, you take R plus 5 and you call this, then if you just print this array, if you print array after this, you will get that array is equals to 1, 2, 3, 4, 5. Now, what is this? Why do I do this? So what stdsort does is it takes this iterator, or you can say pointers in the case of C style array, and it sorts the range it1 it1 to it2 open bracket, which means it1 inclusive and it2 exclusive. So if you look at this array right here, 2 4 3 5 1, then you'll see that this is r, this is r plus 1, this is plus 2 plus 3 plus 4, and then plus 5 is just after 1 somewhere here. So if you take this range, it sorts closed and open, so it will sort this much only. So this range ends up getting sorted into this ascending order 1 2 3 4 5. Any questions? Okay, so the reason I mentioned iterators is that because you can use this with any other sequence kind of any uh, container that is like a sequence. For example, say std vector, or I'm not sure if std double-ended queue allows for this, but std vector at least allows you to sort like an array. So that is why I mentioned iterators. If you use std vector, the syntax would be something like v dot begin and v dot end. Again, this is just, we'll come across this in the container section. So I'm just mentioning this. Now, sort is basically a generic function. Okay. So the thing with sort is that in general, sort will take in 3 arguments. It will take iterator 1, it will take iterator 2, and it will take this function called a comparator. So this function, what does a comparator do? So comparator basically defines a sense of strictly less than. So in other words, if we say this comparator is function f and we pass ab to it, then a fab defines what is a less than b. So fab must satisfy the following properties. Faa must be false, because I mean, a strictly less than a? Is 2 strictly less than 2? Well, is 2 strictly less than 2? Hello?
No, no.
Yeah, no, no, right. So obviously 2 is not strictly less than 2, 2 is equals to 2. So f of AA must return false. So yeah, you get it. Then if f of AB is true, if this is true, then obviously this is not true. Like if A is less than B, B cannot be less than A at the same time. That is obviously not possible. And one more thing it must satisfy is if FAB is true, if FBC is true, then FAC is also true. Which means that if A is strictly less than B, B is strictly less than C, uh, then A is strictly less than C. If you like, in mathematical terms, basically this is called irreflexive. Uh, this is this is called anti-commutative. Forgive my terrible handwriting. And this is called transitive. Well, I assume everyone already knows this from their at least maybe school days or you know maths classes. So these 3 properties together, you can prove that this is enough to define the sense of A less than B. So in like by default, if you have heard of default arguments, so basically the default value of this function is basically your standard sense of less than, like 1 is less than 2. But you can pass other functions to it. For for example, if you wanted to sort in, say, descending order, then you can pass a function, say, fab, and then you can say return uh, a greater than b, right? So now this will return true if a is greater than b, and now you will get a descending sequence. So if you now pass, say, sort r plus 5, and then you passed f, now you will get 5, 4, 3, 2, 1. Because as you can see in this function, we have defined that this function is true if a is greater than b. So put a before b. So strictly less than means a comes before b. So put a before b if a is greater than b. The default value of this function is a less than b. So put a before b if a is less than b. So like this, if we play around with this function and we make it return different things, we can sort it in different ways. Okay. So there are many complex ways to sort an array. And there are problems which also use this property. I think there is a blog post which discusses the problem of scheduling machines, like scheduling jobs on a machine, if you have ever heard of this problem. So there is a rule called, I think, Johnson's rule or something, which makes use of this. Anyway, it's a little advanced stuff, but you can read up about it if you want to. The most important is it must satisfy these three properties, which is irreflexive, anti-commutative, and transitive. Okay. So the time complexity of this algorithm is n log n. Well, if you have heard of merge sort or quick sort, which are the more advanced sorting algorithms, you will know like why this is O of n log n. But yeah, this is pretty good actually for our purposes. If you're interested, STD sort internally it uses something called intro sort, which you've probably never heard of, even I didn't. But like it's kind of a combination of quicksort with some other sorting algorithms. You can read up about it if you want to. There is another kind of sort called stable sort, which internally uses merge sort, but I will not be going into that. I will provide you links to read more about the algorithms we didn't discuss. So, any questions? I covered a lot of things in one page, so if you have any problems, you can ask about it now. There is a lot of silence today. Uh, okay, so if no one is asking any questions, I'll assume you understand what I said, everything about here. Okay, so let's look at the next algorithm. This one is STD is sorted. So this is very simple. It just checks if a sequence is sorted. Not much explanation required here. It just checks if like if you give 1, 2, 3, 4 to it, it will say yes, this is sorted. If you give 2, 1, 3, 4 to it, it will say no, this is not sorted. Pretty obvious stuff. And again, as before, we can pass this comparator function and define some strictly less than. And now we can ask it to say it is sorted only if the elements are in descending order. We can say things like this. Uh, Example usage, again, it's like is the the syntax, I mean the arguments for it's the arguments for this are exactly the same as the previous one. The sorry, yeah, the arguments for this are exactly same as the previous one, which is iterator one, iterator two, and this comparator function. Again, this is optional. You can exclude this and we'll assume that you mean increasing sequence. Okay. And the time complexity of this one is often. It takes linear time because it will basically this is kind of the same as saying for int I equals 0, I less than n, I plus actually I less than n minus 1, I plus plus, and just if a I is less than ai plus 1. Basically checking this. It's basically this function does the same thing. Nothing different. Okay. Uh, so any questions? Okay. Uh, Next slide. So now we are looking at two interesting functions. These are called lower bound and upper bound. So what lower bound and upper bound do is basically they are implementations of binary search. Okay. Uh, the important thing. Okay. By the way, have you guys come across binary search yet in your classes? Just raise your hands. I mean, if you have been taught binary search already.
Like college class.
Yeah, yeah. College class, or if you know it from previously, then also you can. Have they taught it in college class, like in your C++ classes yet? This binary search thing?
No, I don't think so.
No. Uh, okay. I mean, mm, okay, fine. You can put your hands down. It's once. So I mean, binary search is a simple idea. Basically, if you have a sorted array, say 1, 2, 3, 4, no, 1, 2, 3, 4, 5, 6, let's say, and you want to ask where is the element 3. So if this is sorted, you can divide it into two halves. Then you can ask, is 3 less than 4? That is true. So we can discard this half and we can only look in this half. Now you divide this half in, say, two ranges, 1 and 2, 3. The important part is this must be exactly close to half. So now you check, say 2. Is 2, no, is 3 less than 2? No. Then you can just discard this part and discard this, and eventually you come at 3. 3 is equals to 3, so you return this. Basic idea, divide array in half and discard whichever half does not contain our target. So you can prove this will take log n time because every time we are halving the size of the array, and in the end we'll get just one element. So, 2 to the power x equals n. You will come across this later in your C classes, I'm sure. No need to worry about it. So yeah, so basically what lower bound and upper bound do is lower bound refines the first element in an array which is greater than or equal to the target value. So if you say you are looking for x, then say uh, lower bound will give you an iterator, or you can also say pointer to position I, first I, such that if a of I is equals to y, then x is less than equals to y, and it returns first such I. Of course, as I said, this will only work on a sorted array. Binary search does not work if the array is not sorted. In some sense of the word sorted, like in some sense of strictly less than. For simplicity, let's just say we are talking about ascending or descending. Uh, okay, so let's just say we are talking about ascending only. No need to go into such complications. So if you have, say, an array, say 1, 3, 5, 8, 9. So let's say you're searching for, you say, give me lower bound 6. Okay. So lower bound 6. So this will return an iterator to 8. Okay. So you'll get this iterator, and now if you dereference this iterator or pointer, you will get 8. And that is because, well, 1 is less than 6, that is not what we want. 3 is less than 6, again not what we want. 5 less than 6, again not what we want. But 8 is greater than 6. In fact, 8 is greater than equals to 6. So this position is the first one which satisfies the requirement. And if we had something, we had say 6 in here, then instead of 8 it would give 6, because 6 is greater than or equals to 6. In fact, 6 is equals to 6. So 6, this position is the first one which satisfies the requirements. Now, upper bound gives us the first element in an array which is strictly greater than the target value. And that means if we ask for upper bound of 6, now we will get 8. Because 6 is not strictly greater than 6. Obviously, 6 is equals to 6. 8 is strictly greater than 6 and is the first such position in an array. And the good thing is it will find this in log of n. And that is very much helpful in a lot of problems where we need to find elements quickly. Uh, I will provide a list of practice problems after the class. Sometime after the class, I'll provide a list of practice problems where you can see how to use these functions. Okay. So the syntax for lower bound and upper bound, again, it is basically, yeah, it's similar but not the same. So lower bound, iterator 1 and iterator 2, because it will search in the range given by iterator 1 and iterator 2, open bracket, important. Then your target value x, which means you're looking for some element which is greater than equals to, or greater than in case of upper bound, greater than or equals to x. And then again, optionally, you can provide comparator function. Okay. So if you have, say, some array of size 5 and you're looking for the element 6, okay, yeah. 1, 2, 3, 4, 5. If you have an element array of size 6 and you're looking for 6, you can just call lower bound. This array plus 6, then you can search for 6, and this will return you a pointer that is array plus 0, 1, 2, 3, array plus 3. And now if you dereference this array plus 3, you will get 6. So that is how it works. And it is exactly the same for upper bound, except it will give you strictly greater instead of greater than equal. Questions?
Can you explain any use case?
What?
Like, where would this be particularly useful?
Okay, so wait one sec. Let me just so let's say you have a problem. So you have a problem which is like you have some array. Okay, you have some array which is some, say, 1, 6, 7, 12, and it's given that ai is less than equals to ai plus 1. So you have some sorted array of size n, which is, say, less than equals to 10 to the power 5. Okay. And now I ask you Q questions. Okay. Q questions. And each time I ask you, what is the smallest element in A that is greater than equals to X? And I'll provide you X every time. So I can ask you, say, question, say 6, and then you'll have to tell me the answer is 6. If I ask you question 3, again you'll tell me the answer is 6. If I ask you question, say 8, they will tell me the answer is 12. Okay, and now these questions can go up to less than equals to 10 to the power 5, which is pretty big. And assume that you have to answer these questions in the order that I asked them. How will you solve this?
Yeah, that is directly using the lower bound.
Yeah, exactly. You can find the answer directly using lower bound in O of log n time every time. And that means the complexity will be q log n. But see, if you try to use linear search instead of binary searching, if you use linear search every time, it will become O of nq, which is obviously not going to pass.
Right.
See, yeah, so lower bound makes this really easy. You just have to output lower, actually, you'll have to output by dereferencing this lower bound of a plus n, and then x. That's all you have to do, one liner. No fancy while loop or anything, just one line. That is the power of these algorithms. They allow us to just write one line instead of writing 10 lines. You get it?
Yes.
Okay. And this is our this is another function which is named binary search. So this is just it is basically a function that is just there for convenience. It tells you whether x, whether is x in the array. You know, classic binary search question, is x in the array, and array is sorted. So it just tells you true if the element is present or false if the element is not present. Again, this is basically for convenience, and you can just instead use lower bound or upper bound and just see if it is giving you past the end iterator or not. So if some like oh yeah, so yeah, if you take lower bound and you dereference it and see if it gives you the same value as x, and yeah, if x was really present in the array, then obviously lower bound will return x only. Otherwise, it will return some value that is greater than x. So you can just use lower bound and check. But more conveniently, you can use binary search. That is it. So syntax is the same as for the previous two functions. Binary search, uh, say a plus n x, and optionally comparator. That's it. Mostly you will probably not use this. Mostly you will use lower bound and upper bound only. So I hope no one has any questions on this function at least. Uh, okay, so let's see the next one.
The array should be
Yeah, yeah.
sorted. The array should be sorted or unsorted for the input means.
Uh, okay, so always for binary search, the array has to be sorted. The array must be sorted. This is true for these functions and this function. Array must be sorted, and again, sorted can be in ascending or descending. So yeah, they must follow a particular order, if you get what I mean. It must
Okay.
be strictly ascending or strictly descending. Like usually we deal with ascending only. If you are dealing with descending, then again you have to pass this comparator function. Okay.
We can also just replace the A and A plus n, right?
Huh?
You can also replace the A and A plus n, right? Like interchange the iterators. Is that allowed?
I no, you can't, right? Like because uh, if you put A and A plus n, it is going to be searching in the range A and A plus n open. But then if you do A plus n and then A, then like if you have 4, then A plus 4 is going to be here. It's going to be outside the array. Right. Like,
Yeah,
yeah. You get the problem, right? It's going to be searching in this range instead of like just searching in this range in the reverse order. There are ways to circumvent this. I mean, your idea does work, just not with pointers, but there are iterators called reverse iterators, which can solve this problem for you. And they basically do exactly what you said. They just traverse the array in opposite order, and then you will find whatever you want.
good.
Hmm. Okay, so yeah. So now is again another very simple function, stdfind. And this function just implements your standard linear search. Just go through every position of the array and check if if x is equals to this, x is equals to this, x is equals to this, and just linear search. You know what it means. For I equals 1 to I equal to I less than n I plus plus. Just search. Uh, so it returns the first position which contains a given element, and the time complexity is often, as you'd expect, linear search. The example usage would be find a plus n x. There is no question of comparator here since we are anyway going through each element and checking if it's the same. No question of comparator here because we don't require the array to be sorted in any way. I hope no questions here. Okay, so next function. Uh, okay, so this is another very useful function. This one is just max-min. Uh, so these are two separate functions, std max and std min. So I mean, obviously, it does what you'd expect. If you write max 5 6, this will just return you 6. If you write say max 4 1, it will just return you 4. Again, if you write min 5 6, you write min 5 6, you will get 5. If you write min 4 1, you'll get 4. Sorry, not 4, 1. Pretty obvious function. The time complexity is of 1, but something that a lot of people may not know is that you can actually compare more than one value. So basically, the usage here would be like, say you want to compare three values, then you write this max, then you put curly braces. You put curly braces, then you write 1 5 3, end curly braces, and then close. This will return you 5. And if you write min curly braces 1 5 3, it will return 1. Okay. So this curly braces actually defines something called an initializer list, and basically it just provides a list of values to for this function to check. If you are interested, you can read up more about initializer list. I won't be going more into it here. But initializer list will come back in the containers section when we want to initialize containers. There I'll show you like, I mean, okay. This one, I'll admit I am not sure whether the thing, if you write array, you write like array 5 is equals to curly brace like this. I'm not sure whether the usage here is the same as the usage here, but in effect, it is basically the same. It's basically like passing an array, but like you're not actually passing an array. For that, the next function will help us. Okay. The next function is max element, min element. This one will look within a proper array. Okay. So here, if you have an array, say array equal, no, let's just name it A. A is equals to 2, 10, 4, 6, 6. Then you can use max element A, and then this is 0, 1, 2, 3, 4, 5, A plus 5. So this will return, actually this will return a pointer. Okay, this return a pointer to, since 10 is the maximum element, it will return A plus 1. And then if you dereference this, you will just get 10. So it will give you the maximum value, right? Again, for min element, it is the same thing as basically ditto, same thing. And in this case, it will return just A, which is if you dereference A, you will get 2. Uh, so also it will return to first position, like uh, if say if this was 1 instead of 4, then it would actually return a pointer to, okay, so let's summary B is equals to 21466. Here if you call max element on B plus 5, it will actually return a pointer to the fourth position, A plus 4. Sorry, not A plus 4, A plus 0, 1, 2, 3, sorry, A plus 3. Because this is the first position where you find the maximum element. It will not return the second position. The distinction isn't really important, but just good to know. Uh, mm, Now for this function, I am not sure if you can pass an iterator. I mean, sorry, not an iterator, a comparator. I'll have to check. But generally, I mean, if you're looking for max, you know what you mean by maximum. So like the largest value. Probably you can pass a comparator. I'll have to check. Uh, I mean, the basic difference between max element, min element, and max min is that max min is usually used to compare only, 2 or 3 values, and max element is when you have a proper array or vector. Okay. So this one, I don't think anyone should have any problem. If you have a problem, then you can ask. One thing that everyone should have noticed by now is that all of these functions are basically very convenient replacements of what would instead be like for loops or while loops. Like if you wanted to find the max element in an array, you would have to write an entire for loop and go over all the elements and write if statements. But this function conveniently handles that for you by just in just one line. Okay. So this is really what we want when we are looking at STL. Okay, so the next function we are going to be looking at is this is another simple function which works on arrays and vectors, and well, it just reverses a range of elements. Like uh, if you have say a is equals to let's say 2, 1, 4, 6, 7, and now if you pass reverse here, let's go with a sub range. Let's go with 4, 5. Let's go with a plus 1, and let's go with a plus 3. So sorry, not a plus 3, a plus 4, right? Because again, this is everywhere where we use a pair of iterators, we always use uh, closed then open. We always use this. Okay, so a plus 1 to a plus 4 is this range. Okay, so this will just reverse this range, right, in opposite order. So after calling this function, it will look like a 2, 6, 4, 1, 7. So this range has just been written in reverse order. The very obvious stuff. And like it also allows you to check like one nice way to like instead of writing a for loop to check if a string is palindrome, you can just make some separate. If you have a string s, you make a string t equals s. Reverse this t, like t begin, t end. If you can just reverse this and then check if s equals t. Very simple palindrome checking. Um, but yeah, so I mean, don't pay attention to this. I'll explain it later. But yeah, it's a very simple algorithm. So again, time complexity is linear as one would expect. I am assuming no one has any questions in this because it's very simple. Uh, STD swap. Okay, now swapping is like, I mean, kind of like kind of obvious. Like if you have some a equals 5, b equals 3, after calling swap AB, you will get A equals 3, B equals 5. I mean, that's pretty obvious, but usually, I mean, yeah, swap doesn't come up that often, but it is useful sometimes. The special thing about swap is that, like, there are two special things about this swap. One is that in this swap, you can swap any two objects of the same type. It can be variables, it can be containers also. And it can be even function objects, but we are not going to dive into function objects. Uh, so yeah, it can swap arrays, it can swap vectors, it can swap strings, it can swap anything basically. The special thing about swap is that except for C-style arrays, which is like arrays of the form like A5 equals this, and STD array, which is a data structure which is provided by the STL, which is basically a kind of uh, like it's kind of a wrapper for the C-style array. I'm not entirely sure how to explain what a wrapper is, but basically it encapsulates the functionalities. Anyway, except these two things, the time complexity of swapping two containers is constant time. And that is very surprising. Like if you have two arrays, you would expect that you would have to swap them in like linear time by like individually swapping each element. But surprisingly, this is actually constant time. And that is actually very useful for us because this fact we can use in some very interesting tricks which we'll encounter at higher levels. One very big example is called the small to large merging trick, in which you always merge smaller vectors to larger vectors, and this results in some very nice reduction of time complexity. I will not go into this again. If you're interested, you can Google and read about this the small to large merging trick. So yeah, really the most important point is that this is constant time. And this is like the most major fact about it. I mean, example usage is, well, just swap AB, one liner, nothing special, where AB is two objects of same type. Mm, yeah, I think not any, there isn't anything left to cover for swap. One thing that I want you guys to think about is that how can it be constant time? Like it's kind of surprising. So maybe think about how you can make it constant time. Okay, so what functions are left? Okay, okay. So we'll look now at std fill. Uh, Again, simple functions. So what std, all these functions are just for our convenience that they are replacing long, like little long for loops. It's just one-liners, it makes them. So fill, what it does is say you have some array. Okay, you have some array 5 and it is filled with some garbage values. Okay, like you don't know what it is filled with. And now what std fill is, you put fill, then you say a, then a plus 5, again iterator 1 iterator 2 convention, and then you say I'm going to fill it with 1. Okay, so after this call you will find that a is basically just 1 1 1 1 1, so it fills the whole range with some same value. Again, say you have some array b that is like filled with 2s. Now let's say we call fill on this array, and we're going to fill, instead of the whole array, we are going to fill b plus 1 to b plus 4, I mean open bracket, so, and we are going to fill it with 1. So we will fill this range with 1s, and now you'll find that b is basically 2 1 1 1 2. So it filled up this range with 1s. Okay, very simple function, and complexity is often. Mostly what I use it for is just initializing arrays, like before every, say, test case of some problem. For example, like say you have some global array and then you want to just fill up the first 10 elements every time with some constant value, say 0. So this is like an example usage where you can use it. Uh, did someone unmute right now? Okay, so I think there are no problems. So let's look at the next one. Uh, Now we are looking at std iota. So iota basically starts with some value. Say if I say I'm starting with value 3, then it will fill with as 3, 4, 5, 6, 7, 8, and so on. So it is an arithmetic progression with common difference 1. So you provide the starting term a, and now iota will fill like a plus 1, a plus 2, a plus 3. So say you have some array b, which is just filled with say zeros at the beginning. And now say I'm going to do iota, and then I'm going to fill from b plus 1 to b plus 4, this range. I'm going to fill it starting from 3. Okay. So now what we'll do, 0, then 3, then increase by 1 4, increase by 1 5, and then 0, because we didn't, this is our range. So iota is useful whenever you want to, like, obviously when you want to fill an array with say a common difference. Usually when I'm making an array of indexes, say array idx is equals to 0 1 2 3 4. This is the usual use case. Then I'll write, instead of writing a for loop, I'll just say iota idx dot begin, idx dot end, and then I'll just write 0, and it will just fill it 0 1 2 3 4 like this. Uh, I mean, I think the syntax is pretty obvious. Like iota iterator 1, iterator 2, and then a, which is the first term of your AP. By the way, here also, like, fill is iterator 1, iterator 2, and then whatever value you want to fill it up with, say x. Time complexity of n. Linear time. Wait, sorry, this is not O of n, sorry. This is O of log max a comma b. Yeah, like if you are doing GCD a comma b, yeah. Okay, so uh std, gcd, LCM. Now, these functions are only available in C++ 17 and above. If you know, then like C++ has like it was revised several times. So there used to be C++ 98, then there was C++ 0 2003, then C++ 11, then C++ 14, C++ 17, and now there is C++ 20, and upcoming is C++ 23. You must have found at least these options like on like every online judge. Like, okay, not C++ 20. These two options you must have found on any online judge. Like, you have probably found something written as GNU, GCC, G++, 11, 14, 17. So these are just versions of C++. And these two functions are only available in from C++ 17. This one, this one, this one. From here onwards, it is available. And it does exactly what you'd expect. It gives you GCD A of B, and it uses Euclidean algorithm. So, I mean, I assume everyone knows what the Euclidean algorithm is. Like, uh, GCD A of B is equals to GCD A of A mod B. Then, just continue the steps until you get 0, and then just put it, whatever. You know the Euclidean algorithm, I'm assuming. Uh, so this is just a convenient function to know. You do not need to write your own Euclidean algorithm every time. You can just use GCD or you can use LCM. Uh, if you are using C++ 11 or C++ 14 on your online judge, then these functions are not available. But GCC, like this particular compiler provides double underscore GCD and double underscore LCM, which does the same thing as these functions. So don't worry, you're still covered by GCC. But I would recommend that you use the most recent version of C++ that is supported, that is C++ 17. That is my recommendation. Syntax is just obvious, like GCD 2, 6 will return 2. LCM 2, 6 will return, well, 6. GCD 2, 3 is 1, and LCM 2, 3 is going to give you 6. I mean, pretty obvious. So that covers all the important algorithms we wanted to see. Now, what I wanted to like, I wanted to show the containers maybe in next class, but we still have like 10 minutes left. So uh, maybe I'll cover vector at least. So, but before that, I'll just show you these links. So I will share these links separately. Maybe I'll make these slides also available at a later date. But there are a couple of links you can look at. One is this link, which is like a full overview on the standard template library. You can read it. It's very good, and it covers a lot of what we covered today. It covers iterators, the different data structures, and what is a template. It covers those things. You can read it. And these two links you should go through. Like I like, okay, I mean, you can also not go through it. It's not like it's a little advanced because it's not the official documentation of the C++ language, but it's a very complete documentation. And here, like, you can find a complete list of all the algorithms that are available in these two links. There's a complete list of all the algorithms. And in particular, I suggest you see these algorithms that I've listed here. Uh, I will share this. I will share this after the class. Okay. I've also put another link for container, but you can see this after we cover containers. But this link is a must read for everyone. I would say everyone should read this link. Okay, I'll share the link in the chat. Okay, so let's go back to vectors. Great. So actually for this I didn't write out anything, but hopefully I can just write this out. Next class I will like, make a more proper slides for this. So std vector is our first data structure that we'll cover. Okay. After std vector, we'll see pair and string. So what is std vector? std vector is basically vector is a dynamic array. Okay. And there are a couple of things you can do with it. You can insert element anywhere. Okay. So a vector size can change, unlike C arrays, which have a fixed size which you have to specify at compile time. Like C, like array A has to be 250 elements long. Like it has to contain 250 elements. No such restrictions on vector. You can provide any size, and you can even keep it empty at the beginning. So you can insert element anywhere. You can delete from anywhere. Delete from anywhere. Access anywhere. Just like arrays, you can access any element at any point. And yeah, it has random access iterators, which means, yeah, your iterator can jump between any 2 points in a constant time. So now let's just look at the what is the syntax for this is. So it looks like std vector, and then here you will put angular brackets like this, and here you will name your data type. Okay, the data type which this vector is going to store. A vector can only store elements of a single data type. Okay, it's not like say a list in Python which can contain elements of any data type. In C++, vectors can only contain one data type at a time. I mean, yeah, yeah. So let's just say we are storing integers. Okay. Then you put the name of the vector, and here you can end the declaration actually. So this thing will create empty vector holding int data type. Okay. Now into this vector, we have actually a couple of important functions, which for each container, we'll have a list of important functions that you can use to modify or search in the container. So for vector, the two important functions are uh, push back, uh, push front, push front, and pop back and pop front. So, well, push front, okay, push back, push front, they do, okay, so uh, if we have a vector, let's say it's initially just empty, okay. So push back, this is the back of the vector, and this is the front of the vector, okay. the elements which are like, if you have a vector that is already like 1, 2, 3, then the back of the vector is this element 3. This is the back of the vector. And this is the front of the vector, this element 1. So this is v of 0 and this is v of 2. Now push front, I mean push back, what it does is inserts an element at the back of the vector. Okay. So if I now did v dot push back, by the way, the thing here is that we'll write this name, then we'll write a dot, and then we'll write the function name. Okay. And then we'll pass any arguments to it. This dot is called member access operator. Uh, have you have all of you been taught what a structure is in your C classes? Can anyone just unmute and tell me? Anyone? Have you been taught what a structure is? Like,
we haven't.
Yes.
uh, okay, so it seems some classes have and some wait. Like some of you have been taught. Okay, so anyway, so for those who don't know, basically like structure is basically a collection of data types and functions, and like some collection of data type and functions. And this member access operator basically allows you to access any data type or any function that is within the struct. Obviously, in C++, we don't use struct, we use class. And then there is the whole thing of visibility with private, protected, public, that if any of you have studied Java, you might also know. But let's not get into that. So basically the syntax is like the name of the container dot the function and then the arguments. Okay. So okay, we are almost out of time now, so I'll just cover pushback and then we can end the class. So if you do v dot pushback, and then you put 5. So 5 is what we want to push to the back of the vector. Okay. So now to the back of this vector, we are putting this element 5. So now v will look like 5. Now again, if we do v dot pushback, if we do say 2, now we are pushing 2 at the end of the vector. So now we will look like 5, 2. Okay. And push front is similar. Uh, if you do v dot push front, say 1. So now we are pushing 1 at the front of the vector. So now you will have v is equals to 152. I believe that pushback has constant time complexity. This is of 1, and popback also is okay. So popback is basically v dot popback. Popback has no arguments, by the way. Popback basically removes the last element from the vector. So popback means if you have this, it just removes this. Okay, and pop front does the same thing, but it removes this like this. So if you do popback now, we will look like 1, 5. So I think pushback and popback are O of 1, but push front and pop front, I'm not sure if they are O of 1 or they are like linear time. Mm, I do not remember, but most probably these are linear time. In general, if you are inserting and deleting from anywhere, the time complexity taken is the number of elements that you have to move back as like to like say if you have this and you are removing this element, then you have to move this much element, you have to move it. Okay, so like, yeah, you have to move it backwards. Like, just imagine taking a block out of a sequence of blocks and then you have to push all the blocks backwards. So that will take time proportional to the movement of these blocks. So if you are like inserting or deleting at the end, you don't have any blocks to push. So the complexity is constant. But if you're doing so at the front, you have to move every single block backwards. So that is going to be often. That is basically the justification. Okay, it's 7:30, so I think I will end it here. Next class, I will be covering all the containers in more detail. Okay. And it would be nice if before next class you read this link. Okay. So this so the class is over now. Like if you want, you can leave. Okay. So if anyone has any questions about the class today, they can ask right now. Okay. And Anubhav, if you have any announcements to make, you can also make.
Yeah, like no announcements from my part, I guess. So the next class will be a continuation of this class, right? The STL.
Yeah.
Okay, so hopefully that would be on Wednesday, right?
Yeah, that would be on Wednesday.
Okay.
Why is it appearing so big? What the hell? How do I reduce the font size?
Meanwhile, if anyone is having any questions regarding the entire logistics or today's class or any other class. Well, right now over here. Okay, then let's meet on Wednesday itself.
Okay.
Please stop the recording.
Yeah, I'll do that.